Thanks. It's a pleasure to be here. Thanks to the organizers. Sorry for being late to my own talk. So I'm going to talk about tropical surfaces, or tropical geometry in higher dimensions. And so I think after Ilya and Matt's talks, we are all fairly convinced that tropical curves are useful and interesting things to study, so in enumerative geometry and for divisors and linear systems on curves. And so, well, what I want to say in my talk, one thing is to, well, give some definitions, and to, for non-singular tropical spaces in higher dimensions. And the theory of matroids will play some role in this definition of smoothness. And so I won't give much background in matroid theory. We've seen some talks. I'll try to avoid any combinatorics that we won't really need. But the lesson I want to sort of give throughout my talk is that these objects that are locally built out of matroidal fans, matroidal spaces, behave like smooth algebraic varieties in some cases, which is kind of strange that this combinatorial condition gives us that behavior. And then I also want to talk about, well, we saw divisors on curves, but divisors on surfaces, and, well, and curves on surfaces. So, well, the construction of tropical surfaces. And finally, I want to talk about a formulation of Noether's formula in tropical geometry. So this formula, classically, before we go on, I'll just say, because by the end of my talk, it probably will get maybe kind of rushed, that, that in classical geometry, this formula for a surface is sort of the first or easiest case of Herzberg-Riemann-Roch. So we saw Riemann-Roch for curves. And what this basically is Herzberg-Riemann-Roch for the trivial bundle on a surface. So it has a sort of simple expression. So this is my compact algebraic surface. And it's some formula that relates the, well, holomorphic Euler characteristic of my surface to these invariants. And I want to give a tropical formulation of this and say when we can prove it. And, well, the motivation is this, hopefully, leading to a theory of Herzberg-Riemann-Roch more general tropically. So this is just one simple case of something we could hope to generalize from the world of curves. OK, so, well, to start off, I'll tell you how we'll build these tropical spaces. And to start, let's just look back again at tropical affine space, this Tn that it's been denoted. So this is just going to be sort of the extended real numbers to the power of n. So I add in this point at minus infinity. This is what you do if you use the max convention. If you use the min, then you would add in infinity and take away minus infinity. And so we've seen already before that this space is sort of stratified in some way. It has some sort of partial boundary, or it has some boundary, some partial compactification. And I just want to keep track sometimes of, if we have a point in Tn, what coordinates are of negative infinity. So what part of the boundary this is on. So this is called the sedentarity. So this is just all of the i's such that xi of my point is minus infinity. And it's a subset of 1 up through n. OK, because, well, we've seen already for curves that different points in tropical curves, these leaf points, which were sort of supposed to be out at infinity, they kind of had a different behavior than points on the inside. OK. And, well, so this tropical affine space, I won't give the details by what I mean by this trop map, but you're free to think about tropicalization as you wish. So whether you take limits of amoebas or you want to take valuations of coordinates, that this is, if you tropicalize affine space, we of course get Tn. Okay, so I mean, if you're thinking about valuations, you extend, of course, val of, okay. Well, I take minus valuation of 0 is minus infinity. I use max, so I have to take signs with the valuations. Or just log of 0 is minus infinity. And we saw also in the last talk that, well, there were tropical linear spaces, right? So classically, a linear space is still just an affine space, and they looked nothing like the space Tn. They were much more complicated objects. So what we want to build for some theory of tropical manifolds is spaces that are locally built out of affine space, but with taking into account all these possible different models that we can have. So the simplest situation is when we have a fan tropical linear space. So this is the same as saying a fan tropical linear space. Where? I haven't defined anything yet. They're going to be the same thing. Okay, so we saw linear spaces in the last talk, which were, okay, these are, well, on one hand, you get a tropical linear space if you tropicalize an actual linear space. Okay, but it's also much more general than that. And fan means I have a, well, something which is a tropical linear space, but it also happens to be a fan. So it has one, it can be equipped with some fan structure. Okay, but it has at most one vertex. You satisfied? Okay. So basically, I said what I wanted to write down already is that I'm not going to define for you or show you how to construct a matroidal fan for any general matroid. If you, those of you, a lot of you maybe know already how to do it, but just to say that so one way to get examples of such spaces is to just tropicalize a linear space with constant coefficients. Okay, so I'm not going to describe the construction of how to get a general matroidal fan, but an example of this, if you take L, that's, okay, so let me be ambiguous again with my fields and how I tropicalize. So if you're working over a non-Archimedean field, then you want to say defined with constant coefficients. Or if you're working from the point of view of limits of amoebas, you'd say I take a constant family of linear spaces and I tropicalize that. So then this trop L, of course, sits here, like I said before, and it's an example of a fan tropical linear space. Okay, so actually it turns out that, well, any tropical linear space locally is a fan tropical linear, locally is a matroidal fan, so it's a fan tropical linear space. We saw some examples in the last talk, so let me just put one more, that example up again. So if we take L to be some generic plane in C3, so say defined by, well, I won't write down an equation, but and we can think that, okay, I have, if I look at my L intersected with the 3 coordinate planes in C3, I have maybe these 3 lines, and I also have some line at infinity. Okay, and when I tropicalize, so this is sort of my L and with these 4 distinguished lines, and when I tropicalize, I get this fan that was drawn already. So this is in now T3. So the theory of matroids is more general than the theory of linear spaces. So the theory of these matroidal fans is much more general than this example that I just described, but I won't have time to go into it, so we'll just leave it like that. But there is a completely combinatorial construction to come up from a matroid to some geometric object, and that is, well, it's a tropical object. So if I equip a matroidal fan with weights 1 on all the faces, I get a tropical variety. And these are the tropical varieties that seem to behave like smooth things. Okay, so let me give the definition then of a more general tropical space using these matroidal fans. So this is a definition due to McCalkin. And so like I said, what we're going to do is build sort of a manifold, but not in a differentiable sense because these things are not at all smooth. Okay, and we're going to use these pieces, and our coordinate change charts are going to be integer affine transformations. So let's just write this down. So X is going to be, well, first of all, Hausdorff topological space. And like in usual manifold theory, we'll have some atlas. So we have some covering open sets and some charts. And the first condition is, well, we want the image of this chart. Well, it's going to be to some T big N, but we want it to land in some set V alpha, which is going to be a fan, is a tropical linear space. And this should be a homeomorphism onto its image. Okay, and the second condition, so I said on our overlap maps, we want them to, on the overlaps of these open sets, we want our coordinate changes to be integer affine transformations. So this map here is given by, maybe we don't need a map to be defined on all of, let's see, T and beta if our open set that U alpha intersect U beta doesn't land somewhere on the boundary. So it's by partial defined integer affine maps from Tn beta to Tn alpha. Okay, so what do I mean by an integer affine map? Well, we know what an integer affine map from Rn to Rm is. Okay, and I just want to extend it continuously. But my points at minus infinity have to have somewhere to go. Okay, so they have to go to somewhere at minus infinity. And the third condition is just some finiteness condition on, which is really a condition on the atlas, but it can also just kind of restrict what types of spaces we're allowed to have. And since, okay, maybe I won't give the condition, but I'll just say one thing that it prohibits. And you can ask me later if you're interested. So for example, if this was T, and I wanted to remove some point A in the middle, that's not my point at minus infinity, this is prohibited. So, and other things as well, but this is just one example. Okay, so these will be the spaces that will sort of play the role of tropical manifolds or smooth tropical, I don't want to say smooth tropical varieties. We'll see some things which are not algebraic, maybe at the end of the talk, but that fit this description. And yes?
Sorry, so for the first condition, so for the alpha, you want the alpha to be an open embedding, right?
Yes. Yes, an open embedding, and it's a homeomorphism onto its image.
Okay, so, but it's not about this
No, onto its image. I said it, but I didn't write it. I'm sorry, thank you. So it's a, yeah, open embedding. Okay, so we saw abstract tropical varieties in dimension 1. These are our tropical curves, and this definition actually gives us the same thing. It just turns out that in dimension 1, having an integral affine structure is the same thing as having a metric. Okay, so integral affine structures in dimension 1 is just, it happens to be the same thing. Well, the only thing that's maybe sort of not so clear is where this sort of matroidal thing comes in. And really it's, so at a vertex of a curve, so a metric is the same as an integral affine structure. So along the edges, if we have an integral affine structure, it's the same as having length. And, well, at a vertex, right, so of our abstract tropical curve, I should think that the valency is going to determine for me, so let's put 4 in to be a little more interesting, the chart which I have. Okay, so that it has to be to some kind of tropical line, right? A fan tropical linear space will be a tropical line with one vertex, but that's sort of determined by, up to some simple things, up to, determined by the number of rays at that vertex. Okay, so we've seen other examples also already, even in dimension 2. So we had this exercise that now I hope everyone has really done it, of Ilya's, to, or in any dimension actually, but we saw this example of TP2. Ilya gave the answer. It looks like a big infinite triangle. Okay, and so even though over a field, CP2 has no boundary, but here our tropical manifold might have some boundary, so which is these 3 edges that were our distinguished coordinate axes. And so let's just make precise what we mean by, or what the boundary looks like, because it actually gets stratified as well. So remember we had this notion of sedentarity, which was what points had some certain coordinates equal to minus infinity. And so this is just, the boundary is, of course, just the set of points, x, such that, okay, so let me write it first and then explain what I mean. It says that this is strictly greater than 0. Okay, so sedentarity here is, of course, dependent on coordinates, right? And now we're trying to do something with manifolds, which is coordinate independent, but just take any chart, and its image in the chart will have some sedentarity, and I just want how big it is. Okay, and if you look at a connected component, pardon? Yes, it follows if I should have written one simple thing that this is a, let's say, simple here. So simple referring to the matroid simple. So it has no loops or double parallel elements, double point. Okay, and then this boundary gets stratified. There's some irreducible boundary divisors, which come up when you look at, well, points of sedentarity larger than 1. So let's just say, since we'll talk mostly, I mean, this works for things higher than, of higher dimension as well, but the boundary of x, if we subtract also the points of sedentarity larger than 1, then we get some connected components, and each connected component is a tropical curve, abstract tropical curve, like we've seen before. So here, these are the points of higher sedentarity, and we have some tropical curve, which is, well, it's just R. It's kind of boring in this case, but and all of these sort of tropical curves have their leaves, their endpoints at infinity removed, but we can put them back in. Okay, and we'll call their closures again an irreducible boundary divisor. So take the closure in X again, and irreducible boundary curve. Okay, so we have some tropical curves already on a surface, an abstract tropical surface. And well, of course, there are more. We have curves inside the surface as well. So what are curves that are actually in the interior of a surface? If we have some subset, and under this map, it goes to a tropical curve in your V alpha, or some piece of a tropical curve in V alpha, and in each chart, the weights on the overlaps are consistent, then you get a tropical curve in your surface. Okay, so let's call those interior tropical curves. If it is in every chart. And so remember, a tropical curve has, of course, weights, and so we need those weights to just agree on overlaps. Okay, and a tropical cycle, which we haven't seen, I think, yet, is going to be the same definition of as a tropical curve, right? So remember that we have positive integer weights on a tropical curve, and a cycle is just we allow those weights to maybe be negative. Okay, so it's the same definition of one cycle. So let me cheat and just say it's a tropical, well, it's more general than tropical curve, but the only difference is that we allow integer weights on the edges. So we still have the same balancing condition. Okay, and then so we saw divisor groups for curves, and the divisors on X. So these are sort of the Weil divisors, codimension 1 cycles. So I'll write them like this. It's, well, consists of the interior cycles. So these are interior cycles. And then we have, for each boundary divisor, we can take any multiple of it, our irreducible boundary curve, and we have some cycle. Okay, so we have divisor groups as well. And we can actually also talk about PIC, so we can take a look at this modulo rational equivalence, which is interesting and complicated, and I'm happy to talk about it, but I won't talk about it in my talk. So there's some examples of calculating PICs of, well, more interesting surfaces, so K3 surfaces, for example. Okay, so maybe the first thing that I want to say about this smoothness is a theorem of exactly this equivalence of these divisors, these V divisors, and so-called tropical Cartier divisors. So I'll state it more generally. I've only given definitions for surfaces. So V divisors meaning codimension 1 tropical cycles. And, well, let's call them. And tropical Cartier divisors are equivalent. So what do I mean by tropical Cartier divisors? Well, we've seen divisors from functions in maths talk, and we saw some modifications. So we had other tropical functions also in the CS talk. And, well, a tropical Cartier divisor, you should just think it's the exact same definition, except locally you're allowed to give some function. It has to be a tropical function, so piecewise integer affine. And then on the overlaps of these sets where you've given the functions, they have to be compatible up to not a piecewise integer affine function now, but an affine function. Okay? So a Cartier divisor is a collection of well, tropical rational functions. But let me just write continuous piecewise affine. Okay, and this is a fact that's true for, well, smooth algebraic varieties, this equivalence of V divisors and Cartier divisors. And so somehow this fact of being like a locally fan tropical plane, which is, I mean, or, you know, which is even more general than being a tropicalization of a linear space, can be made toroidal, so having no real geometric or algebraic geometric meaning. And it is, has these things in common with smooth algebraic varieties. But there's one remark I should say, is that we can talk about effective divisors. So effective V divisor would be just all of the weights are positive. So if we're in the case of a surface, it means you have a tropical curve. Okay? And an effective V divisor, well, we saw last talk, there was this difference between tropical regular functions, which are given by polynomials, and tropical rational functions. And so we can use the same idea here, that an effective Cartier divisor is one that is given by regular tropical functions. Okay, and there is no equivalence in that sense with effective ones. So what did I want to say? That there are effective tropical V divisors which are not effective Cartier. Okay. Oh, and I meant to actually pause after I gave this definition and mention some other work in looking at tropical geometry in higher dimensions and its relation to what we saw so in maths talks, is that there's another approach that's sort of similar to the, well, we had the metric graphs, and then we just had graphs where we thought about the metric just being weight 1 on all the edges. And so there's sort of alternative to this, or similarly with that comparison, there's a theory of Dust and Cartwright of so-called tropical complexes. Which, if you think in terms of back to the curve scenario, these would be like the curves with metric 1 everywhere. So these are coming from, or not necessarily, but they do come from the dual complex of some regular semi-stable models. And there's a whole theory of this that, and also divisors on these that works quite nicely, and it's sort of very similar to the sort of, I guess, the discrete graph theory, version of tropical geometry on graphs, and this is sort of maybe more the continuous one. So here we have possibilities for well, varying the tropical structure and having moduli, but it's a lot more complicated, and Dustin has been able to do lots of good stuff with these tropical complexes. Okay, maybe just one more thing to, and before I say this, one more thing to convince you about some smoothness of, or this relationship with this definition and smoothness. First, to do that, though, I should tell you that now it's quite easy to intersect tropical intersection theory for curves or for one cycles and surfaces. Now, once I told you that every codimension 1 cycle is actually a Cartier divisor on my space, I can use the theory of Cartier divisors to, just as in the classical setting, to define intersection numbers. So on a surface, if I want to, and C1, C2 are 2 1 cycles, I can define an intersection pairing because I have this theorem. Well, so this intersections approach was first introduced by, so there's maybe so many names to put here to attribute. McCalkin, Allerman and Rao, myself, and I think probably also Katz, yes. In different, I think, yeah, well, at least in the relationships between different definitions. But for this simple situation of of 1 cycles in a surface, we can use the theory of Cartier divisors, which was, I think, sort of suggested by McCalkin and made rigorous by Eller and Rao, to intersect 2 curves in the surface. We just express one as a Cartier divisor, right? So this means we have then, we restrict that function to our other curve. Okay, so I take this function, so I have a Cartier divisor that gives me my cycle C2 on my surface. I take that function, I restrict it to my other curve, and now I can do what Matt was doing. I have a piecewise linear function on this abstract graph. Now look at it on C1, and I just count the breakpoints with their multiplicities, okay? And then that gives me the intersection product. But so this works great in dimension 2 everywhere except for self-intersections of boundary curves. And this is just sort of lucky because, I mean, we know that a tropical piece, the tropical zeros of functions are sort of strange. They're not actually where it attains tropical 0, which is minus infinity, right? They're sort of these breaking points. And so my function doesn't necessarily, even if I have C1 times C2, the function for C1 doesn't necessarily vanish on itself. But if you have a boundary divisor, then that is exactly what happens, and you need something different. And in higher dimensions, actually, so I won't write down any theorems or anything, but it turns out you don't need to just use Cartier divisors. There is a nice intersection theory on these matroidal fans that lets you intersect any cycles without using any kind of Cartier divisors. So there's another, well, it's slightly stronger than what you have in classical algebraic geometry because we have an intersection product defined on the cycle level, but we have something that's defined sort of on algebraic cycles for smooth tropical manifolds. Okay, and so to continue on with these smooth properties, I just want to show you a version of the tropical adjunction formula for curves and surfaces. So X is going to be a compact tropical surface, so smooth tropical surface. And I'm going to take C. So I need to use some adjective here, and I'll explain what it is in a second. Is locally degree 1 in X. This is very important. Then, so this is just an abstract tropical curve, so it's a graph. Its first Betti number, which we've seen before as representing its genus, is equal to what the classical adjunction formula would say. So maybe the only thing that I should explain to you now is, well, what this is and what this condition means. But first of all, we've seen the canonical class for the case of a curve. And the kx for a surface is a one cycle. Supported on the one skeleton. And with weights, it looks the exact same. Are very similar to the case of curves, being just the valency of the edge. I'll explain what I mean in a second, minus 2. So the valency here is I have an edge, and that means it's in a two-dimensional tropical surface, so it has a certain number of faces coming off, and that valency is just the number of faces. If you read it like this, that's exactly looks like the definition for curves. And what's maybe not obvious, but it's a one-line proof using a definition in an axiom in matroid theory that this is actually balanced one cycle. And what does it mean to be locally degree 1? It means that my tropical curve in every chart has to look like a tropical line inside of a tropical plane. Okay, so I can't, in the same coordinates, this has to be a line in a chart, and this has to be a plane. And just some quick remarks. Well, the adjunction formula classically is, well, somewhat stronger than this. It's kind of the adjunction inequality. So if you have you put the geometric genus here, it's always less than or equal to what you get here, the arithmetic genus. And equality if and only if the curve is smooth. However, tropical curves, there is absolutely no inequality. It can fail in both ways. So if I think that, well, if I calculate this, sometimes it can be, in fact, negative, and the curve is irreducible. So this is some. So if we remove the locally degree 1 condition, the adjunction formula well, it can fail sort of in two ways so that we don't even get an inequality. And the curves that I mentioned where this might be negative, but they're irreducible, this is sort of an indication that these tropical curves are not realizable, and that was some joint work with Erwan Brugele that I won't talk about. Okay, so I don't have much time, so I won't talk about how to prove this, but it's very simple, and it's just a combinatorial argument that, well, when the curve is at the boundary, you see that it's just totally obvious. You just do the Euler characteristic computation. It's a good exercise. And then what do you do when it's not on the boundary? You do what we saw in the last talk, and you do the next thing, which I'm going to talk about, and it's called tropical modifications, and that will send your curve to a boundary curve in a new surface. Ah, yeah. So that's a very good question. So, well, on one hand, this is sort of more general. This can be coming from something which is not at all tropicalization. But yeah, there are ways to see it as being the canonical class. Yeah. Okay, so we saw some tropical modifications in the last talk, and I maybe need to start speeding up. So, well, what is this? If we take again, some curve in our surface, then we know that, well, if any one cycle, we know that there is some Cartier divisor that defines it. Okay, and what we can do, we saw with Lucia that if you have just one regular function, or maybe even a rational function, you can take the graph, do this modification. You take the graph, you add in the extra faces so that you get something that's balanced, and then you get another tropical variety. And so basically, you can do this tropical modification in each chart and cook up a whole new tropical manifold. And the reason why you get a tropical manifold, well, you have to show that you get charts and that everything glues. But the reason why it's smooth is because of this locally degree 1 condition. Okay? And a tropical modification always also comes with a map back to the original space. So it sort of like looks like the notation for a birational transformation. So where this x tilde is a new tropical surface. And it has one more boundary divisor. Let's call it C tilde, but it's the same metric graph as the original C. So how should you think about these? Well, we've seen tropical modifications actually for curves in Matt's talk as well, where he had his, say, his tropical elliptic curve and got to add in a bunch of leaves or take them away. And he said that if you come at it from the semi-stable model perspective, it's just like you take a point on the special fiber and you blow it up. Okay, so what this is doing, it's the exact same thing. We get to blow up a divisor. Okay, if we're in the situation of some semi-stable models, this is just like blowing up a divisor on the special fiber. So this notation that looks like codimension 1 blowups, which don't usually make sense or don't make any changes, is that. And that's how we should think about it, that these operations of tropical modifications make no changes to the, well, they change the geometry somewhat, it changed the underlying space, but pretty much all invariants stay the same. So on one hand, this lets us construct some new tropical surfaces, but they're just a different model of the same surface that we had. So the next thing is another operation that will actually help us build some neat examples. So what's the tropical sum of surfaces? Well, it's basically you have two surfaces, and you want to glue them together at some parts. And what you can do is if you have two boundary curves that are compatible in some way, you can glue them together. And this is this is a tropical analog of a fiber sum or a symplectic sum. On one hand, it's like the symplectic sum because we get a whole family of tropical surfaces that we can glue. Okay, so we need two tropical surfaces. And I want some irreducible boundary curves. So maybe let's write it like this. And I want that these two curves to be, well, isomorphic. And I want to fix some map between them. So I have fix. So I want this to be, well, a tropical isomorphism. It should just think that it's an isometry of metric graphs. So it's the same underlying graph, and I have the same way of identifying two graphs, and I have the same. Okay. And suppose also that neighborhoods of these two curves inside the surface okay, well, let me change this first. Gives what I'll call the tropical, or from this neighborhood, we can construct the tropical normal bundle of CI. So we didn't talk about, Matt didn't talk about, well, tropical line bundles, but basically all the ingredients are there of divisors and Picard group and everything. And so if we follow the usual classical constructions for our dictionary between bundles and line bundles and divisors and Cartier divisors and everything, then we can see that this gives us an element in the Picard group of CI, just by the usual classical way. So we need to suppose that these are in this Picard group of my curve. Let me call it just C, since it's the same as CI. If these are inverses, then we can form the tropical sum of these two surfaces along these curves. So I should have said compact, although it's not necessary. Things might actually be easier if it's not compact. Questions? No? Ah, thank you. Yes. Yeah. Okay, so what does something like this look like? Well, can't draw a very good picture, but a neighborhood of the curve surface might look something like this, where this is my curve on the boundary. These are some other boundary curves that touch it, and maybe this is some part of the interior part of the surface. Okay, and this just happens to be the right condition that I can put these tropical manifolds together and get a new, or these surfaces together and get a new tropical surface with charts and everything. And well, there's some extra choices to make, but I won't get into it. But we can just, we then wrote some notation like this, just like the notation for sums of other manifolds. And it depends on some choices, so I won't explain what they all are, but we can talk about them after if you want. So you can actually get a whole family of these surfaces. Is there a question? No. Okay, and I have to go very quickly. Maybe I don't get my 5 minutes because it was my fault that I was 5 minutes late. No? Who's Ethan?
No, it's okay.
Are you sure? Okay. Okay, so just quickly some examples. We saw floor decomposed curves. You can talk about floor decomposed tropical hypersurfaces. And these are just examples of sums. TP3 or R3, it doesn't really matter. I won't draw any pictures because they'll be very bad. But basically the point is that, remember, for a floor decomposed curve, your Newton polygon, the subdivision that was dual to it, had these levels in the subdivision. And so it's sort of a subdivision that contains, of your Newton polytope that contains these sort of vertical hyperplanes, or any kind of transversal pair of hyperplanes. We can also, using this, just following the usual, well, symplectic construction for summing and summing and blowdowns, so we can form contractions of some -1 curves. And you just, maybe you have a -1 curve E in your surface, and what you should do is you sum with some plane along an L that has the same. So E is some rational, is a tree with the self-intersection -1. And L should be the same as E. So I'm not giving many details, but I'm trying to get to the more interesting stuff I wanted to say. And the last thing maybe I should just point out is that with the sum construction, you may leave the algebraic world. So there's a sum in symplectic geometry, and there's a fiber sum of manifolds, but generally you can't do this. And well, if you can even take the self-sum of some tropical manifolds, so I could sum this. This is a tropical Hertzsprung surface sigma 1, so just P2 blown up in one point. And I can take the self-sum of this surface along these two curves. Their normal bundles are opposite. And actually, so let's call this E and L. Or I call this sigma 1. This gives a tropical model of a Hopf surface, which is well, a complex structure on S1 cross S1. So complex S1 cross S3. And these are maybe among some of the simplest examples of non-algebraic complex manifolds. So they were discovered by Codera, I think maybe as the first examples of non-algebraic complex manifolds. Okay, and well, one thing that maybe it would be interesting to see is an application. So there's, well, symplectic sum formulas for Gromov-Witten invariance. There's not, well, in general, there's no sum formulas for Welschel invariance because there's problems with relative invariance and everything. But we know that tropical geometry is good with enumerative geometry, and actually these floor diagrams and the enumerative geometry that we get out of that, it's kind of like a Caporasa. It's just a tropical version, formulation of the Caporasa-Harris formula. And it comes from basically breaking your variety into a bunch of different pieces. So it can be seen as a sum formula where you sort of start to break P2 along the normal bundle of lines over and over and over again, and you put 1 point in each part. And so maybe from this tropical sum of surfaces, so, there are obviously difficulties, but maybe some more general floor diagrams. So there's already floor diagrams relative to a conic of R1-Brugale, but maybe it would be possible to give some more, I don't know, but it fits with the topics of our mini courses. The last thing I want to say is just go back to this Noether's formula, which I said is the first basic case of having Hertzberg-Riemann rock for tropical surfaces are in higher dimension. And how should we formulate it tropically? So instead of the holomorphic Euler characteristic, one should actually put the topological Euler characteristic. I'll say why here. I told you what the canonical class is now and how to intersect it, sort of, with itself, modulo some boundary intersections. I say very quickly in a second how we get this C2. And, well, we all know how to divide by 12. And so why should we put the topological Euler characteristic here? This comes from the theory of PQ, tropical PQ homology of Eaton, Barkett-Zarkov, Mikhalkin, and Zarkov, that their PQ the ranks of the tropical PQ homology groups in nice cases should give us the Hodge numbers of, well, a member of a family in a degeneration. Maybe there's other ways of seeing this too with that. No? Questions? Okay. It says that we should put H0Q to be equal to of a complex surface should just be replaced with the Betti number of H-cubed Betti number of the tropicalization. And C2, okay, I don't have much time, but there's ways to give really nice just closed combinatorial formulas for these higher Chern cycles. And basically, classically, this is just the Euler characteristic of the entire manifold. So here's holomorphic Euler characteristic, and here's topological Euler characteristic. And if we think that we have our tropical manifold locally being built up by these linear spaces, sort of like each point, okay, sort of, well, virtually, we can think that there's some, above it, there's some, well, linear space, or perhaps complement of hyperplane arrangement, linear space in C star n. And it turns out you can express this C2 as just a well, weighted collection of points. So it's a zero cycle, but we only really want the sum total, the degree of the zero cycle, that are in the zero skeleton of the surface. And this is a matroid invariant of the underlying matroid of the local model at that point. So this is, well, plus or minus the beta invariant. It's basically you take the reduced characteristic polynomial of your matroid, remember it's a fan linear space at some little x. So there's some underlying matroid, and I take that reduced characteristic polynomial of that matroid and evaluate it at 1. That gives me the Euler characteristic of the complement of a hyperplane arrangement coming from the matroid. Okay, so maybe I won't write it because I'm way over time now, but I just want to say that this formula, we can prove it, or I can prove it in certain cases, like you start from toric surfaces, tropical toric surfaces, you perform modifications, and you are allowed to do sums. And on those operations, you can control all the invariants, and you get this formula. But there should be some deeper, not so just, not counting faces. So Dust and Cartwright can also do it for complexes, but these are sort of two different types of spaces. There's some overlap on them. But there should be some argument deeper than just counting the faces. One way maybe is that this is some kind of Gauss-Bonnet formula that we saw curvature of tropical varieties in Jean-Jacques' talk, and that would be a much nicer interpretation. Okay, thanks. Sorry for going over time.